All right, here we go. We are on chapter 15. This is the last chapter in C101, and we are going to be looking at electrolytes, acids, and bases. We have talked a little bit about electrolytes in previous chapters, but we're going to bring it back together a little bit today in this first lecture. So I have a little bit of a demo, and the questions up top, it says, what type of solution will complete the circuit? All right, so if you have any light that you plug in, okay, you know electricity has to flow through the wires, and usually there's a wire that makes a complete circuit. So it goes one in and one around it and on the way out. So you can actually cut that or buy a conductivity tester like this one right here, and you can see that it does not complete the circuit just how it is. And you can see that the light bulb is not on, okay? So I have two solutions. Both of these solutions are just plain water right now. We'll put it in both solutions here for us. And you can see that in neither of these solutions does the light bulb go on. Let's just look at two different things that we can put in here and see if they will actually cause this solution to complete the circuit. So first thing, I just have some sugar packets. Okay, so I poured a couple into here. Let's pour the sugar into this one. Stir it up, and we can see that the sugar does dissolve. Okay, so it goes into solution there. But is that something, once the sugar dissolves, can it complete the circuit? So let's take this, put it in there. Does our light bulb go on? No, it doesn't. All right, so a sugar solution did not turn the light bulb on. All right, in the other beaker, there we go, I'm going to add some salt. So this is just some normal table salt that you would have. Season your food, pour that in this one. And again, it did not turn it on when it was just pure water. Let's see what happens here. Wow, look at that, light bulb. What was the difference between the two solutions? See, as soon as it comes out of the solution, it doesn't work. It has to be in the liquid for it to work. Put it back in the sugar solution, nothing. Salt solution, yeah. All right, let's take a look and see about the two different solutions. What's the difference between the two of them? All right, pull this out. Pull this out. There we go. All right, moving to the next slide. Here we go. There is a difference between the salt and the sugar, okay? And the salt, we would call an electrolyte. Electrolyte is just a medical chemical term for ionic salts. You've probably heard of like the sports drinks and making sure after you do a lot of exercise that you replenish your electrolytes. All right, so electrolytes are important. They're used in conducting electrical impulses. And acids and bases, which we're going to be talking about this chapter, are a set of electrolytes. So this gets back to the conductivity thing too. In order for a solution to conduct electricity, there has to be a way for the circuit to be complete, and that's through electrons. Electrons have to be able to flow into the solution. When you have sodium chloride, that's the little picture there on the left, and you put it into water like we just did, it breaks apart. Not only does it dissolve, it dissociates into ions. So you have sodium chloride now forming sodium ions and chloride ions. Those ions allow the circuit to be complete, and then we were able to get that light bulb to go on. So dissociate. All right, so that gets us to what it means to dissociate. Something that dissociates not only dissolves into solution, but it also breaks apart into ions. Now, what two substances did that as far as our light demo that we just did? The sodium chloride broke into ions, sodium ions and chloride ions. However, our sugar solution just went from sugar as a solid to sugar aqueous. There were no ions present when we put the sugar into solution. Same thing with this example of ethanol here. So here's ethanol. This is another molecular compound that will dissolve in solution. Okay, so it mixes in there completely. You probably can see that there's probably going to be some hydrogen bonding going on between the OH on the ethanol and the water molecules. However, the ethanol does not break apart into any ions. So this would not be an electrolyte. It would not cause the light to go on. All right, so what are things that are electrolytes? Any soluble ionic compound, and then also you will have any acid and base are also electrolytes. And in this chapter, we're going to be looking at acids and bases in more detail. All right, so that answers that. Let's look here at this table here. We have a bunch of electrolytes, non-electrolytes listed. I want you to go through that list, see if you can identify, based on what we just talked about, which ones would be electrolytes and non-electrolytes. So take a little pause. We'll come back with the answers. All right, so what did you pick out for being electrolytes? You should have been able to identify that first one as an acid, acetic acid in the name, so that should be an electrolyte. Other electrolytes you're looking for anything that's an acid, a base, or a soluble ionic compound. I see sodium sulfate there, that would be an electrolyte. Sodium hydrogen carbonate, also an electrolyte. Hydrochloric acid, you see from the name there, HCl, and ammonium nitrate. All right, even bonus points if you can also write me the formula. We have Na2SO4. Carbonate is CO3 negative 2. Na is +1, hydrogen's +1, so this would be NaHCO3. Hydrochloric acid formula is given ammonium nitrate, NH4NO3. You can see for the ones that I wrote down there, they are all ionic compounds. They have a metal and a nonmetal. In all these cases, it looks like our nonmetal is a polyatomic ion. Those would all be considered electrolytes. The remaining ones then would be molecular compounds, and we would call those non-electrolytes. So methane, oxygen, carbon dioxide, acetone, and we also have sucrose there. That's our sugar example. They may dissolve in water, however, they would not conduct electricity. They would be considered non-electrolytes. All right, looking at those ones that we did circle as electrolytes, you can see, okay, the ionic ones, there's two acids as well, hydrochloric and acetic acid. Now, if I had the light bulb thing and I had it set up with HCl and with acetic acid, CH3COOH, would the light be the same? If I had the same concentration of both of those acids, what would be different? And there is a difference. This one, the light would only be partially on. Whereas if I had the same concentration of HCl, the light would be full light. And why is that? And it has something to do with the equilibrium. So we're going to go back to a little bit of our previous chapter with equilibrium, but let's go and look at the next slide where we talk a little bit more about some definitions. All right, we're going to talk about types of electrolytes. So we now have categorized things as either an electrolyte or a non-electrolyte, but in the electrolyte category, you can also talk about strong and weak electrolytes. Strong ones, okay, by definition, completely dissociate. That means the entire electrolyte has broken apart into ions. A weak electrolyte only partially dissociates. All right, so here is an example, and you can see the light bulb difference between, in this case, we have HCl, which is a strong electrolyte, and hydrofluoric acid, HF. The light bulb goes on. You can see a little bit of light from this image here. However, it's not as bright as the strong acid. Now, you have ions, okay, so it dissociated, but not all the way. So there's not as many ions per amount of acid here. We can write this out a little bit, what's going on, okay? So if we have HCl, and we're adding this to water, we completely, so I'm going to draw just a single arrow here, go and make ions. Now, what ions are present here? You see some anion there, you see some Cl minus, and you also see something that looks like H3O plus. Now there's also a lot of water molecules in here too. They're just not written in. Only the ions are being shown here. What is this H3O plus? I believe we have talked about this previously, but let's just make sure we all understand that. When you have H plus being formed, which is what happens when HCl dissociates, H plus and Cl minus, that H plus will join up with a water molecule and it will form H3O plus. So your concentration of H plus is also equal to your concentration of H3O plus. H3O plus we call the hydronium ion. So you don't usually just see any H pluses freely floating around. You would see what happens when the H plus joins up with the water and makes the hydronium ion. All right, so HCl completely dissociates. It breaks up into ions. It is a strong acid. Our weak acid example, HF, you put that into water. I'm going to draw a double arrow to show this is not completely to the right here. This is in equilibrium. If you look here, okay, in our picture here, we can see the light's only partially on, and we see a couple things in solution. We see some F minus, and we also see the other product is what happens when that HF breaks apart. It forms H plus. H plus would join with the water, so we see some hydronium. Okay, so you see the hydronium right here, but you also see mostly a lot of molecular HF molecules. There is a ton of this left over at equilibrium. So for the first example with the strong acid at equilibrium, it is very product favored. Okay, we have pretty much just Cl minus an H3O plus. For the other example, when we said it's a weak electrolyte, not all of it breaks apart into ions. A lot of it will stay as the molecular compound over here, HF. So some has dissociated, but not all of it. And that is what is the definition of a weak electrolyte. Now, just based on that, you should be able to tell me, since we were just talking about which one lies to the left and to the right, which one has a larger equilibrium constant. The larger equilibrium constant, and oftentimes when we're talking about this in terms of acids, we'd be talking about the equilibrium constant of acids. So equilibrium constant for acids, which one is larger? Well, since HCl is a strong acid and it lies completely to the right, the K equilibrium for HCl is much, much greater than 10 to the positive third, which we said is what happens when it lies to the right-hand side. Compare that to the equilibrium constant for HF, and this is 3.5 times 10 to the negative 4. So much smaller value. That means the equilibrium lies far to the left-hand side for the hydrofluoric acid, since it is a weak acid. All right, another important question. When I say, oh, it's just a weak acid, does that mean it's something that you should easily just play with? You don't even need goggles or gloves since it's a weak acid. You should be able to answer absolutely not. That has nothing to do with how dangerous it is. Okay, when I say it's a weak acid, that has to do with how it dissociates. However, HF is highly corrosive. Okay, it's a contact poison. I'll just write corrosive poison. In fact, if you get this on your skin, it can do some damage. It can penetrate your tissues pretty easily, and then it interferes with nerve functioning because the fluoride ion actually will interact with the calcium and precipitate out. So then you're now losing some calcium ions from your blood and in your tissues, and so it can be very dangerous. So if you're using hydrofluoric acid, which some people might have used it to do etching with glass, you want to make sure you're in a very protective area. Usually we're in a glove box type situation where you want to make sure you don't have any exposure to the hydrofluoric acid. So just because it's weak, that has nothing to do with how dangerous it is. It has all to do with how it dissociates into solution. All right, moving on then. let's look at these beakers here, and I want to just label them. So go ahead and look at these 3 beakers. Now that we've talked about strong, weak, and non-electrolyte, can you figure out which beaker belongs to what category? Okay. All right, good. All right, ready to go back again. All right, so here we go. You should have had a couple seconds to now sit and label these. You will see NaF, all right, sodium fluoride. When you put this into solution, it completely formed ions. It completely broke apart. So we know it dissociates, so it's an electrolyte. And since I don't see any NaF left into the solution, I would say this is a strong electrolyte. All right, next we just were talking about HF, so that should have been a little bit of an easier one, but you can see that it does form some ions. In there I see one F minus and one H plus. All right, but most of it is still the molecular acid HF, which means this would be an electrolyte and a weak electrolyte. And then the last category, or the last beaker here, we have F2 being put into solution. Put it into water. It might dissolve in there, but we have no ions formed. There's no positive charge anything. There's no negative charge anything. That means it's a non-electrolyte. All right, so that's good for that. Hopefully that makes sense. We can now move on and start looking at some definitions of acids.